We're going to continue on with Faraday's law. Which, as we've seen it in two different forms, the EMF, what's called the induced EMF, being equal to a negative rate of change of magnetic flux through some area, or we can also write that as a curly electric field, the electric field integral, path integral around a closed path. Integrate the electric field, then curly electric field around the closed path, and you will get the same thing as the rate of change of the magnetic flux through the area bound by that path. Okay, and we did some problems last time kind of applying this. I want to do a couple more examples of some applications with this that you will be having to do for homework, either for Friday or next week. And I want to just take a little aside here and talk about something we briefly mentioned before, but a distribution of current called a solenoid. Okay, so when I say a solenoid, what do I mean? Well, we've seen a coil. We've seen a loop of current, for example. If I draw a current loop this way, conventional current going that way, then that's going to produce inside the loop, it's going to produce a magnetic field pointing out, and then elsewhere it's going to produce a magnetic field pointing in the opposite direction. We've seen this dipole pattern. This is a magnetic dipole. So we've seen this pattern of magnetic dipole fields before. If I draw the loop edge on, where the current is coming, conventional current is coming out at the top, going in at the bottom, then you find the magnetic field along the center line pointing in this direction, magnetic field elsewhere pointing in the opposite direction, or along the perpendicular, I should say, pointing in the opposite direction, and then kind of pointing like that elsewhere. Okay. And then we can even apply that to a number of turns of loop, or turns of wire, loops of wire. And we get basically the same result if the coil is thin compared to the radius. Okay, and all we've done is essentially multiply by n to give us the total magnetic field. Well, when we have a solenoid behaves a little bit differently. A solenoid is a coil, but it's a very long coil. Okay, a solenoid is a coil of wire that is much longer than it is wide. At least for how we're defining it. And so, kind of like a long tube like this. If you imagine wrapping a wire around in a very long tube, you find something like this. And what happens is that you have, again, current coming out at the top, going in at the bottom. Inside the solenoid, you're going to get a magnetic field, and the direction is going to be given the same way. And so inside we have a magnetic field pointing in this direction. Okay, so this is the magnetic field inside the tube here. It turns out that outside of the solenoid, if the solenoid is very, very long compared to its radius, then if you're at an observation location out here, you can actually work it out through superposition. There's going to be a lot of cancellation going on, that the magnetic field made by each individual loop, okay, you have to take all those into account, but a loop over here is going to be producing a magnetic field. Let's see, it's going to kind of be pointing that way. And a loop over here make a field pointing in the opposite direction. And the more loops you have, the greater cancellation you get. And outside, B outside is equal to 0, or it's approximately equal to 0. Again, it's going to be dependent on how long it is compared to the width. But the longer you can get this compared to its radius, due to this cancellation effects due to superposition, you'll actually find that the magnetic field is approximately equal to 0. The magnitude, I'm not going to go too much into detail, but the magnitude of this, and you can do more formal proofs with this, by actually applying Ampere's law, where, remember, Ampere's law depends on a loop. And if you imagine a loop that kind of goes down into the solenoid and actually pierces, you have then current piercing through this imaginary loop. You could relate the current enclosed by that loop to the magnetic field inside and actually calculate it. Okay, and if you want details, it's in the book. But all we need to know for this particular example we're going to talk about is that the magnetic field inside is non-zero and uniform. It's actually uniform inside as well. So a solenoid you can actually use as a way to produce a uniform magnetic field, just like a capacitor you can use as a way to produce a uniform electric field. Outside the solenoid is equal to 0. Okay, just the factoid that we need. Given that, let's think about a question. Here's a solenoid that is running through the inside of a metal ring. Okay, so I've got a long solenoid. Current is running through it in the same way we drew it over there. I'm not sure if you can see this, but the conventional current is coming out at the top, going in at the bottom, so it's wrapping around like this. It's producing in the interior a magnetic field pointing along the positive x direction. Okay, I've got a metal ring that's in the YZ plane, and I have just made the solenoid coaxial with the ring. Okay, so if I were looking at this head on, just to get the geometry right here, if I'm looking down, sort of down the length of the tube, that's the solenoid, and then I just have a ring surrounding it. Okay, and then this is the positive x-axis would be coming out towards us from this point of view. Okay, so given that, we have a solenoid of radius of 2 centimeters. The ring that surrounds it has a radius of 10 centimeters. The magnetic field inside the solenoid is uniform, and it's half a Tesla, 0.5 Tesla. Outside, again, as we said, the magnetic field is approximately equal to 0. What's the magnetic flux through the outer ring? What's the magnetic flux through the outer ring? Okay, so we have just a bare majority saying answer number 2, although there are 2 other popular answers. One is 0, and the other one is 4. Well, first of all, we're just calculating the flux, and we're not calculating a change in flux. Now, there is a magnetic field here. If it's not changing, it actually isn't going to produce any EMF. Okay, in fact, the time derivative of it would be 0. But if we just want to find the flux, that's just B times the area. Okay, so we are going to have some magnetic flux through this region because there is some magnetic field. But where is the magnetic field? Only in the solenoid, right? Everywhere else, it's equal to 0. So if I'm thinking about calculating the flux, let's draw it again, looking down the solenoid, sort of head on here. Then I have magnetic field coming out in this region, and magnetic field out here equal to 0. So if I'm looking at this total area over the whole ring, what part of that area is going to contribute a non-zero flux? Just the solenoid, right? So only the area of the solenoid is going to matter here when we're calculating the magnetic flux. Think about dividing it up into pieces. Again, what this summation is telling us, or this integral is telling us, is we're summing up by dividing up the total area, which is the area of the ring, into little squares, okay? And then thinking about the magnetic flux through each one of those squares. Well, for every single square out here, the magnetic field is 0, right? So when I sum up the flux, I'm going to get a 0 plus 0 plus 0 plus 0 plus 0 plus 0. So I keep adding up a flux of 0 until I get to the interior here where the solenoid is jutting through, okay? And only that area is going to contribute a non-zero. So the total flux then is going to be the magnetic field of the solenoid times pi times the radius of the solenoid, not the radius of the ring, squared. Okay, and that should give you, what did we say it was, 2.5 Tesla? 0.5 Tesla pi times 0.02 squared, which is answer number 2, I believe, 6.3 times 10 to the minus 4 Tesla meters squared. Okay? Questions there? But most people got that, but some confusion about what area to use. And the way to think about it is you're thinking about summing up the flux of the entire area, but just in a lot of that area, B is equal to 0. So only this part is going to contribute. Okay? Yeah, that's right. The magnetic flux over the whole ring turns out to be equal to the magnetic flux just over the center. Because again, it's like having two separate areas and you're adding them together. The flux over this, circle-shaped piece is all going to be 0, plus the flux of the interior, which is giving us that. That just gives us, 6.3 times 10 to the minus 4. Okay. Other questions? Okay.